In this lab, lab 4, we will be examining the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. We will use fundamental principles to create a computational model of the motion and compare to 2D position data. We will also graphically describe kinetic and potential energies of our computational model. The results I got was that my computational model's position graph was very similar, almost identical, to the tracker video's position graph. Also, the graph of total change in energy for the system was a constant line at 0, meaning the energy principle was preserved. Fundamental principles in this lab were Newton's second law, which is also called the momentum principle, which was F net equals m times delta V over delta T, where m is mass, and our energy principle, which if our system, if our spring and our mass is our system, then there is no energy transfer because that is our system. So delta E should be 0. And delta E is our change in kinetic energy, plus our change in potential energy of gravity, plus our change in potential energy of our spring, and they're all 0. Our initializations were that the calibration stick was 0.7, and that was given, 0.7 meters. I put the origin where the spring was attached, and made that 0, and then our initial position was therefore negative 0.104 meters in the x and negative 0.63 meters in the y. Frame dt was 0.0095 seconds. First thing to do was find our Ks, which is our spring stiffness, and from our position data in the y versus t, I found 3 oscillations, and the time was 4.573. I divided by 3 to find our period. And I used my period of a spring equation, switched it around, and found that K equals 6.83 newton meters. In order to find F net and Fs, you need to know that F net equals the force of the spring plus the force of gravity. The force of the spring is K times our compression factor times a unit vector L, which just gives it a negative, puts a negative to the equation because it's in the downward direction. F gravity is mass times G like normal, and I put those into Python. Now S, which is our compression, is L minus LO as seen in the picture. At full stretch, we were given that it was 0.7 meters, so that is when Fg equals Fs, and I rearranged the equation to find LO, which was 0.123 meters, and I plugged that into initialization on Python. Calculating energy and position data, Newton's second law is Vf equals Vi plus F net over m times delta T, and that's just rearranged. I put this into Python, and once you have your V final, you can then find your position final from the initial position plus velocity times time. Now, I also had to find, for the energy principle, initializations of K, U, G, and US, which are K is 1/2 mv squared, which is our final velocity found, and UG is mgh, where h is compression factor, and US equals 1/2 ks squared. I also found the deltas of all of these to then put into the energy principle, which is the addition of all of those, and they should be 0. Now, comparing all of these, I will actually show you my model. Now, the red is the mass of my data from Tracker, and the blue is the computational model. As you can see, they vary a little bit, but they still go in the same appropriate direction. The error where they are not exactly together is also seen in this graph of the position data, where blue is our model position in the y-axis and red is our tracker position. And they are almost exactly, but there is some variance because when I'm marking the center of mass in tracker, I may not be exactly on the center, which will give that different position data. But they are similar, which is what was hoped for. Now, this is the code I imported in order to get those, and this is where I imported the data from Tracker, and this is where I graphed the plots. Now, our energy graphs, where I have U, G, which is green, I have delta K, which is red, and I have delta US, which is blue. I would want to get our yellow line to be 0, which is our total change in energy, delta K plus delta UG plus delta US. And this is in fact true for my computational model because I did get a yellow line to be 0. You can barely see it, but it is 0 along here, and that's because our energy principle was preserved, that there was no transfer of energy into the system, which was true. And here's where I graphed it in Python. Now, what does this mean? Is the energy principle satisfied? Well, I just showed you that because the yellow line of delta E total is 0 on the graph. If there are no interactions, then delta E should be 0, which is true. What if we use X data for our period instead of the Y data we used? Well, our X data had a very different position versus time graph, so our period will be different, which was about 1.63 seconds. Now, my Ks will then be different according to that equation, which means that then my force of spring will be less than what our spring in the Y was. Why Ty over Tx? Well, gravity and spring act in the negative Y and positive Y directions, so it would be appropriate to use Ty and stiffness Ksy. The pendulum acts in both directions, so when you're actually finding the period, you do the equation listed there instead of the equation I used, which is the period of a spring. So thank you for watching.